Hello MC300. Today I want to show you how you can do a truss analysis using a program called RISA2D. It's a really awesome, powerful program that you can get for free if you just go and Google RISA2D Educational. You can download the free version of this pretty awesome software. All right, so let's go ahead and open this up and do a truss analysis from our example problem in class. It makes that funny noise on startup. I'm not sure how to get rid of that noise. But when you open it up, you can see this drawing grid. You can either hide the grid or like this, toggle on and off, or you can change it. All right, so let's go ahead and change this grid to match our dimensions from our problem in class. So we had 24 feet in width and 6 feet high. So do 24 by 1, 6 by 1, hit OK. And this will snap to our new drawing grid here. All right, so the next step we want to do is put our joint coordinates in. So I like to click on joint coordinates over here in data entry. And then we can start naming our joints. So we had A was at 0, 0, hit enter. We can see this is starting to populate in our drawing grid. The next one was B, which was at 8, 0. C was at 16, 0. And D was at 24, 0. E we had as 16 and 6. And our last one, F, was 8 and 6. All right, so we can click out of here now, and we can see that we have all of our joints are now populated within our drawing grid. So let's turn off the grid, and next we want to get our members drawn. So you can do this one of two ways. You can either draw your members over here, click Draw Members. It's going to give you this window. We don't worry about the area, the moment of inertia, or the modulus right now because we're not going to be dealing with internal stresses or strains. We're just dealing with force, so these don't matter at this point. What does matter though is the end conditions of each of our members. So we have the left end I and the right end J. So these are not fixed because in a truss we assume that all of our connections are pinned at the end. So we're going to say pin pin and then hit OK, which then opens up our drawing tool. So now we can click on a joint and draw each of our members just like that. It's a really quick and easy way to draw members. Okay, and you can just hit escape to clear out of that drawing tool. And I'm going to show you also how you can draw your members using this data entry tool on the right to get our last 3 members in here. So let's turn on our node so we can see where our members are going to. We're going to go over here and click members. All right, so now we can see all the members that we've created. So let's name these. Let's change these names to AB, BC, CD, DE, EF, and AF. And if you want to add another member, you simply just hit enter and it goes to the next line. And so let's make this one. So we want BF, and this is going from joint B to joint F. Hit enter and then we can see that member just populated. Okay. And then we want member BE was going from joint B to joint E. Right. That one just populated. And then our last one is CE. So we'll do CEs from CE or from C to E. Click off, and there we go. We have our last member. If you go up to the top, you can turn on the member labels to make sure that we had everything done correctly, which this all looks good. Okay, so the next step is getting our boundary conditions or our supports in place. So if we hit Modify Boundary Conditions, we'll get this window where we have a free, fixed pin, or roller support as options. We had a pin at A, so we're going to click on pin, which shows that we had a fixed condition in the X direction and fixed in the Y. All right, which means that there was a reaction in the X, reaction in the Y, and it's free to rotate. All right, so that's by definition a pin support. So we're going to hit Apply Entry here. By clicking on the joints, click Apply, and now I can click at joint A, and now we can see our pin support at joint A. Now let's get our roller here, so we'll click Roller. We have free in the X, fixed in the Y. If your roller, for example, is oriented the other way, say you wanted to be fixed in the X and free in the Y, you can also change that here. Okay, but the default, if you click roller, is fixed in the Y translational direction. So click apply, and then we're going to click on joint D. Now we can see our roller is applied at joint D. All right, last thing we need is our applied load. So first, before we apply our load, let's just make sure our units are correct. So we'll go up here to the top, click units, and we can modify the length, which is in feet, which is good. And then the force we had in pounds. So we'll go ahead and change that to pounds and then hit OK. And then we'll go over here to apply joint loads. And we'll click on this. This will give us our pop-up window. It says this is a load. The load we had applied for this example problem was in the Y direction, so we'll drop this down to Y, and it was a minus 1,500 pound magnitude here. Apply load by clicking on the joints, hit apply. Now we can just click on joint B, and we can see that this fourth arrow is now populated on joint B with a minus 1,500 pounds magnitude. The way these are applied in RISA is that it's with the tip of the arrow is always applied to the node, whereas we draw them in class typically with the tail here at the node pointing downwards. But that's how they're going to look in this instance, but it still has the same effect. Okay, so now we're good to go. We have everything set up in our truss that we can solve. So we'll now go up here to solve. This results window pops up down here. We can say joint reactions, and this will give us our external reaction forces. So joint A, we had 0 pounds in the X direction and 1,000 pounds in the Y direction, which is good. That matched up with what we got in class. And then at D, we had 500 pounds in the Y direction. Also awesome. All right, and the next one we can click on is member forces, and this will give us the internal axial force in each one of our members within our truss, every single one. Notice that there's no shear and no moment for any of these cases, all right, because in a truss, all the members are axial. You'll also notice that each of these members has 5 sections. It's broken down with the same force in each one. It's a lot of data to filter through. So if you want to get rid of that, you can go up here to global, and this will just change the number of sections that you wanted to analyze. And you can drop this all the way down to 2 is the lowest you can go. This is just the number of locations along the member that is conducting the analysis. But for truss, since it's axial, it's the same throughout. So let's just drop that down to 2, hit yes. It's going to clear the results. And then we'll go ahead and solve again. And then our window pops right back up. All right, and now this is a little easier to read. Only 2 data points per member. And this looks good. This is exactly what we got in class. So over here, you can see the zero force member CE was in fact correct. This calculates it as 0 pounds going through member CE. All right, and then in class, we also found that member, let's look at AF, this compression member here, we found was 1667 pounds, which is good. That matches up. One thing of note, RISA, their sign convention is opposite from what we use in class. So in RISA, so AF here, which is a compression member, is reported as a positive value. So there's one thing to note, RISA reports compression members as positive and the tension members are reported as negative in this program. But just make sure you know that in MC300, we do it the other way, all right? So compression members are always negative and tension members are always positive. But you can still check this in RISA to make sure your magnitude is correct. And then just remember that in RISA, it's going to be flipped, okay? But don't do that when you're doing it by hand. Otherwise, you'll be incorrect. Okay, but just remember, AF here is a compression member. In RISA, the sign is flipped, okay? But yeah, so that's how you do it. Pretty straightforward. Only takes a few minutes to go ahead and do an entire truss analysis using this program. So feel free to use this at your disposal if you want to calculate internal forces in a truss. Okay, thanks.